Now that we're done with our shrunken head conversation, we can record. Okay. The last homework was due today. It's been extended to midnight. Nothing due on Tuesday. Project 5 is due on next Thursday. And then the final exam is optional if you turn in a course evaluation receipt. Open book, open notes. There's 5 problems. You get to choose 4. And you get 5 points for completing the course evaluation. There is no practice final. I finally got done writing the 380 practice final. That didn't involve me just giving them exams. Okay. What are we doing in here? We're doing imagers. We're going to talk about the photodiode and some of the technology behind it today. I may get sidetracked because the first people who did this I actually worked with. Basically what we're doing here, we have a PN diode and we're going to use a photodiode. So remember the calculations we did yesterday, we found out that the band gap of silicon is just right to allow to absorb photons in the visible light. Since it can absorb photons in the visible light, what's going to happen when it absorbs a photon is it's going to produce an electron-hole pair. An electron's going to get excited out of the valence band and into the conduction band, leaving behind a hole in the valence band. Now, if this happens in this region, if the photon comes in and lands in the inside of the region, it creates an electron-hole pair. There's a whole bunch more electrons than there are holes, so more than likely it's just going to get absorbed and you're going to lose it. If it goes into the p-doped region, the same thing happens. Because there's so many more holes and electrons, the electron will get absorbed. Now, if the lucky photon makes it into the depletion region, it's going to generate an electron-hole pair on one side of this. So if I get an electron-hole pair here, that's fine. Well, the hole is just it's going to absorb an electron. The electron's going to want to move. What we know, the electron's going to want to move this way. The hole's going to want to move this way. I can't see where the pluses and minuses are on here. I don't have my glasses. So, anyways, they're going to move over, and it's going to start depleting the charge. Slowly depleting the charge in that junction. So the whole idea here is what we want to do is before we actually set up this device to take an image, we have to switch on the device and get a large negative voltage across the diode. So we have a large depletion region on the inside. And we can dope this differently to make the depletion region more on one side than the other. We usually dope them to have a large depletion region on the inside and a smaller depletion region on the P side. And then as the photon comes in, it absorbs an electron with its hole, and you slowly discharge the capacitor. So the capacitance of the PN junction diode. I gotta stop calling it a capacitor. So we're gonna slowly discharge the depletion region. The voltage across the depletion region will go down as the amount of charge in there goes down. And when we read it at a later time, we let the light come in for a little while, a few seconds, a few hours, a few milliseconds, depending upon how fast you want to do it. And we read the voltage level a little bit later in time, and we compare the initial voltage to the final voltage, and that's the amount of signal we have. Now there's things like quantum efficiency. Quantum efficiency is a measure of how many photons actually hit the diode and produce and actually reduce the charge. Some of them don't. Some of them get absorbed someplace else. So if you're like dealing with astronomers, you want the quantum efficiency really high because they get really upset when you lose a photon. And if you're dealing with like a commercial application, visible light, you don't worry so much. You want it to be high enough you can create an image, but there'll always be more photons. Okay, so this is the idea right here to build the photodiode. We've got to have some reset voltage, and we want to reverse bias the diode. So we're going to put the positive voltage on the N side. The positive part of the diode is the substrate. We're burying the photodiodes in the substrate. I need some kind of reset switch in here, and the reset switch is basically going to decide when I turn that on and reverse bias it. Then I'll need some kind of readout on this too. Okay, this is the photodiode, the buried in the substrate photodiode. That was the big innovation that brought about CMOS imagers. It wasn't that hard to do. It took someone saying that, oh wait, silicon sees, let's make it see in a more orderly fashion.
When something has a feature, is it above or feature?
Is it there's things that, and see, that's one of the first things I learned, is that I was sitting there grousing about how horrible this was, that I had this problem that this thing was seeing because the substrate wasn't grounded, and never sitting there thinking about, well, what's the application? Because it would have been partially because it would have been a really lousy astronomical imager. It took tens of years to get it to the point where it was comparable to what we were using in the visible light before. In the IR, we are using those photodiode arrays, similar architecture to what they used in CMOS imagers, but in the visible light at the time, they were doing something much more horrible called CCDs, charge coupled devices. There was such a division between the basic architecture of the cameras that we had two different groups of engineers at Kit Peak. People like me who just worked in the IR, and people like Andy Radine I shared an office with who just worked with CCDs, and Tom Wolf too. Andy was fun. He always said you had to change jobs every 10 years as an engineer. Otherwise, you started driving yourself crazy because you had to go back and fix things that you had worked on originally. And my dad would say that too. His timeline was 7 years. And he said you couldn't stay any place longer than 7 years. He never actually stayed working on one mill any longer than like 4 years. Because what happens is you go back, people forget what they did 7 years ago, and they go back and they start making the same mistakes. And you're the one sitting there saying, wait a minute, stop this, you can't do this, we did this before. And they're going, no, this is the right thing to do. And you go, no, this failed, this is why it failed. And you just find yourself beating your head against the wall. So I've been here 10 years.
7 years is the upper maximum for your dad in any mill, but he was only there, but it had any given milk for mostly 4 years.
Yeah, it was 4 years was the longest, and that was in Prince Albert. We were in Atlanta for 10 years continuously, and the only reason why we got away with that is he was working for Georgia Pacific at corporate headquarters, and he was building 6 pulp mills at the same time. The largest toilet paper manufacturing facility in the world, Crossett, Arkansas.
They were busy in 2020.
They were busy in 2020. So this is the diode. It's a MOS diode, and they're using this in CCDs. And basically what you do, this is just like a MOS capacitor. In fact, that's exactly what it is. But you don't put any contacts for the rest of the transistor in. You just have the gate, the oxide, and you put a positive, you can put a positive voltage on the gate. And if you do that, you're going to create a negative depletion region underneath the gate. And there's your PN junction diode. It creates kind of an energy well. This is the way we can kind of draw them schematically. It's an energy well. We can fill it with electrons as photons, and why is this not working? As photons hit this, they're going to take carriers away. They're going to discharge that, and the well's going to empty. And then you have to read out what's in the well. So fairly simple to build. So this is one of the earlier devices, first digital camera for visible light. And this came out in about 1970, and it was developed by Bell Labs and Kodak and JPL, depending upon who you talk to. Jim Janasik is the one I knew, and he was from JPL.
So every time you want to take a photo,
Yeah.
you have to fill up the well, and then it kind of takes the photo and you measure the difference between the two, how much light.
Yes. Yeah, you got to do a comparison. Now you could, if you really want to do sloppy imaging, you could just measure, you say, okay, it's always going to reset to the same value every time, and just measure what it is at the end.
Okay.
Yeah, but that was never good enough for astronomers.
For like videos, it's doing this just really fast.
Right.
Yeah, since basically using video, it's basically just lots of pictures in a row. Yeah, since frames,
Right.
So.
Yeah. If you're somebody like you're military and you want to see a bomb coming through, like a missile coming through your line of sight, and you want to have a really fast frame rate, then you don't care so much about image quality. You're just, can I see the missile? And can I see it moving with time? And can I see how fast it's moving? Yes. We're going to talk about one of those. Okay, that wasn't one of mine. I was, yeah.
It's really cool.
Okay. Yeah, stunt cameras that move really fast. The Kleinfelder chip that we read about in Project 5, that is one of the, that has like a capability of doing 10,000 frames per second.
My phone will do 960 for 1 second.
For 1 second, and then it fills up the memory. Okay. So for a CMOS imager, the way we read it out looks an awful lot like a memory. We have a reverse bias diode, and usually when we were drawing these sketches of this and when we were first building it, we didn't even draw the diode, we just drew it like it was a capacitor. Because it's a reverse bias diode and we're just discharging the capacitance. What we need to do, this is not the addressing, this is the readout scheme. Let's change that word, Dr. Brower. Readout. Okay, so this is the readout scheme. Basically, first of all, I'm going to have to address it, read it out, reset this capacitor, wait a little while, and I want to read it out. I'm going to need some kind of amplifier on here. And what we used was a SFD, source follower per detector. Just a standard source follower like we learned about in 380. And I'm going to switch when this one is on by putting in I'll get to this, by putting in a row address and a column address. Now, usually when you're reading out of memory, you want to go through and randomly access different points in there. If you're reading out an image, most of the time you want to read out the whole image and do it in an orderly fashion. So what they did is they actually, the earliest IR devices had shift registers in here. And I would just load in a 1 at for the first row, and it would start the first row state machine and read out all the columns, and then it would move down to the second one, second row, and then come back through here and read out all the columns, and just do that repetitively. Fairly simple standard circuits, and So the Aladdin array that we built, the first IR array for astronomy, we had shift registers for scanners, and they were all PMOS. Because PMOS has lower noise than NMOS. We didn't care so much about reading them out quickly. We cared about the noise. And the horrible thing was all the logic was inverted. And the guy who was designing the chip, doing the actual layout in Santa Barbara, he was a negative logic thinking person. And I was the one doing kind of like the circuit design and doing mainly the pixel circuit design. I'm a very positive logic thinking person, and we get into these horrible arguments, and all the polarities of the logic would be wrong. We actually fixed that by putting inverters on every single signal coming into the chip. And then we could talk to each other again. Jim Wallaway. Okay, so this is a CMOS. It's just an XY addressing scheme, and we're going to step through every address in the array at one time. One of the projects I worked on was the first one that had actual random addressing, and I'll show you a picture of that later on. And show you some of the ridiculous requirements they give me. Okay, so for these CCDs, what they have to do, you have a MOS capacitor and nothing else. So what you do is you take the charge that's in one bucket and you pass it to the next capacitor. So on cycle 1, you're going to read out what's here. And it kind of acts like a big shift register. And then you have to take all the charge that's in this next bucket and move it down. And everything gets moved down. It's like a bucket brigade on a fire line or something like that. And you just keep on doing this until finally this charge here ends up being read out. And it requires non-overlapping clocks. We talked about those in 490 in the fall. Clocks that are such that it was a 3-phase clock, and no 2 phases of the clock could be high at the same time. So significant analog timing in there. The other thing that's going on in here is every time I pass the charge from one MOS diode to another, I'm going to lose a little bit of charge. And if I even lose 1% of the charge, I have nothing left when I get to the end of that row, if it's a long row. So the biggest problem they had with these CCDs was something called charge transfer efficiency, CTE. And they usually talked about it in the number of nines, as in 3 nines would be 0.999. So you'd have to have 99.9%. They were usually talking about, to get a reasonable readout, 5 or 6 nines. So it was a really touchy design. The chips were super expensive. Science grade devices, they were, several $100,000 each. Astronomers don't balk too much. The Phoenix instrument I showed you, it had a total budget of around $2 million. We were the 3rd attempt to build this instrument, and this is how it got the name Phoenix. It kept rising from its own ashes, and we finally did it. So that was but the big brunt of the expense is the focal plane. That's where you invest the money, and the optics, and the electronics are kind of secondary. And so for our timing, and Zach asked about this a few minutes ago, if I have a CCD imager, what I do is I reset. Why is this not working again? I reset all. I can't draw. This is the first time that oh, there we go. Okay, I reset all the rows at the same time. And then I'm going to wait whatever my integration time is. And I'm going to wait. And as it's discharged and the voltage changes, then I'm going to read it out again here. and I subtract these two values, and that will be the total amount of signal that I've gotten in that time. I can't really read them all out at the same time, but fairly close to the same time. Now, the CMOS imagers, because it's built in a CMOS process, standard CMOS, instead of the special process for CCDs, we can put all kinds of CMOS electronics in there, any kind of digital thing you want. We had like random access, and what we would do is we'd go in and we'd reset row 1, and then we'd reset row 2, and then we reset row 3, and we would wait a row time between here, between the reset, so we could actually interleave these later. I was the timing person. And then we would wait, and then when the integration time passed, we may be on row 434. So when we get to when we reset row 434, we go back and we read out row 1. And then we reset 435 and then read out row 2.
Okay.
And so you're going to have the same integration time on each row in the image, but you can start resetting them a little bit earlier. And again, you're comparing its reset value to its final value. It waits and then it gets read out.
Is that why if you're fast enough, sometimes you can see pictures of someone taking a picture of like a kid sitting in front of a mirror and they're blinking in the mirror, but not.
Yeah, those are really crazy.
Okay,
The camera like goes like this or something, and it catches them not blinking but still blinking in the mirror.
that would be really hard to do. It might be because of the interleave. It might be because of the interleaving. We'll talk about later. Is that it's taking the top of the picture at a slightly different time than the bottom of the picture.
Yeah.
If they're in two different places in the picture.
Yeah.
Yeah. So yeah, some of the cool things we discovered. We had no idea until we built them. We could actually get the shutter speed fast enough that we could take a picture of a fan and it would look like that was moving and it looked like it was standing still. We could also make the shutter speed long enough that we could take a picture in a dark room. If a room is
The same camera?
with the same camera, you can adjust the timing. If I integrate for a really long time, okay.
Here's what we're thinking of is that you could see his eyes. Oh gosh.
Okay.
His eyes are closed there, but they're still open in the mirror.
It-
It's like the
it-
camera caught just
wow.
right.
Yeah, and it must be scanning this way, or it was turned on its side,
Yeah.
and maybe it's scanning. Yeah, just scanning this way. Yeah.
But it's-
Okay. Slightly different time.
Yeah.
It's super cool.
Yeah. Okay, so it's analogous to kind of like and we'll talk about that when we get to interleaving too, because this was kind of a real problem in the early cameras, early video cameras. If you leave, this integration time is variable, and you can set it. If we set it to our minimum integration time, we could see the fan standing still. If we set it out at a really long integration time, we could take a picture in a dark room that you normally just can't see anything. Just shut the lights down in the lab in the basement with no windows, and you couldn't see a darn thing in there, and you could still take a picture. There is light in there. It's just not as, there are photons in there. There's just not as many of them. So if I integrate those photons for a long amount of time and everybody stands still, you can still get a picture. No, night vision goggles are in the IR. Okay, so in the infrared, what you look like is you're a body emitting heat. And you don't get a real picture of you, you get a picture of what the heat emitting regions of your body are.
Like, these night vision goggles are like they like make everything green.
Well, it depends upon what you can have false color IR. We did that too. And the way but it doesn't make, false color IR doesn't make a lot of sense to humans. as far as how we were used to seeing things. What you would see is the warmer places would be one color and the cooler places would be another color. They use those, Michael Schaefer has this little IR camera in his lab now that's like, you know, it's like $5,000. And for relatively cheap. I'm dumbfounded by how cheap that was. You gotta understand where I came from. And what that would do, you could use that for is if like you had an electronics board and you wanted to see what was overheating and where the hot spots were, you wanted to put heat sinks on them. He's using them to measure the thermal properties of materials. Go figure, he's a mechanical engineer. So he's got some materials that like change state at certain temperatures and he wants to key down to like 0.1 C to figure out what it is. When we built our astronomical cameras, they came out in color, but they were in the infrared. And what we did is we were like they were really black and white cameras, but we took 4 images and put them on top of each other of the same thing. One was in the 1 micron band, one was in the 2 micron, one was in the 3, and one was in the 3 to 5. And we made these false color images that way. And you can look into the star forming regions. One real advantage of infrared astronomy is that you can actually see through dust clouds. So we got to see into the center of the galaxy and see the rings on Jupiter from the ground and do all kinds of cool things. It's like, and we're the first ones doing it. So it's like, what are we gonna look at next? And we come up with stuff. There's a lot of cheap science. Look, this is what this looks like in the IR. No one's seen this before. Okay, so what the problem Zach was talking about a few minutes ago is he has an image of a boy who's looking in a mirror. And you can see the boy's got his eyes open on one side and in the mirror he's blinking. Okay, now this is probably the camera turned on its side. Now what happens here is this row gets reset first and it gets read first. So this is an earlier image. This part of the image happens earlier in time than this part of the image. It may be milliseconds if you have a fast camera. Back when they first started doing TV, this was kind of like a real problem because the cameras were fairly slow.
Yeah, it was like one of those things where you like with the older cameras, they to like sit still for like a solid like 2 minutes.
Yeah, you for like the 1800s, you had to sit still and skip, and you couldn't smile because your expression might change. But the early TV cameras, you know, they're running maybe like around 10 hertz or something like that to do a whole frame. And if a guy's running across the screen and you're getting an image of the top of the screen first and then the bottom of the screen later, he's going to be skewed this way. His legs aren't going to be attached to his body. Something that's moving fast, rapidly across the array. And that's probably what's going on in the picture of the boy, is that as you're scanning, you had the camera on its side, and as you're scanning across, you caught the boy's image at a different moment in time than you did the boy's image in the mirror. Okay.
Even though it's like just like a few milliseconds.
Yeah, a few milliseconds later.
Yeah.
So what they did with the TV standard actually looked like this, is you actually read out a row and then you skipped a row and you just read the even rows first and then you read the odd rows on the next cycle. And that helped to smooth all that out.
Wouldn't that make it kind of more blurry?
It wasn't all that great back then. This is so that was the TV standard, was to do an even and an odd. And it left its mark on imaging from then on. It's like even with the IR images, we had 4 amplifiers that we narrowed down into two channels, and we just called them EDO and ODO, even data out and odd data out. There's a problem with the EDO board. He just had to fix it. It sometimes wouldn't work, our EDO board. So, and it was a wire wrap board, this monstrosity of things that were just basically hooked together by wrapping wires rapidly around other wires. So tend to break, and there was a loose wire in there somewhere.
Oh, no.
And so occasionally it wouldn't work. And so we had, and this was before I started there. They had this protocol. They go over there and whack the board, and then they power it up and try it again. And you sometimes have to do that 3 or 4 times. And eventually you'd whack the board just right, and it would work. I had a calibrated whacking stick that was usually tended to work. It was kind of a superstitious thing, but this Dan Bass came in there, and he was going to be a hero and fix the board. And he went through and rewire wrapped the whole thing, and it never worked again.
Oh, no.
It was his first run-in with Al Fowler.
I imagine Al was not very happy about that.
Al blew his top. Dan's second run-in with Al Fowler was, we had this pump in the lab. It was a nitrogen pump, nitrogen trap diffusion pump for getting the air out of our vacuum chambers before we cooled them down. If you ever let the nitrogen run out of the trap, the liquid nitrogen, it would freeze up, and you'd basically have to take the entire pump apart, rebuild it, re-grease every bearing, and go through. It was about a 30-hour operation straight through.
If you ever let him freeze, right?
If you ever let the nitrogen run out. Dan let the nitrogen run out.
Oh.
You could almost hear the fireballs coming out of Al's mouth from 3 doors down. So that was his second run-in, and this is when he started sweating every time he heard Al's keys. He got a job at he just went back to he got a job doing something else, and then we hired Charlie. Another thing. Okay.
Wait, so is the whole like Fowler Nordham?
No, I don't think.
Different Fowler.
I think that's probably a different Fowler, because before he was at Kit Peak,
I think she says.
I don't know. He was more of a circuit designer than anything else. And he was at Northrop Grumman doing Black Ops stuff and Redondo Beach before he came to Kit Peak. And that's why he knew all the guys at Rockwell and Hughes SBRC. So I don't know what he was doing before then.
Okay,
but it wasn't flash, it was more in imaging.
So he probably isn't the same Fowler.
And probably not the same Fowler.
Might be related to the religion of the Fowler.
Yeah, I don't know. That Al was from the Ozarks.
Huh.
Yeah, he was the kid who his inventive days when he was younger, as he was running a still in his dorm room. He was more of a I'm sorry, I don't know. I'm getting me way off track here. Okay. So inside the pixel, we have a photodiode, but that's not the entire pixel. There's area in here that's readout electronics. Why is my pencil not working? So there's area in here that is readout electronics. This is part of the pixel where you're not gathering light. So one of the figures of merit for this device is, if this is my aperture, this is the actual light collecting region. The stuff that's cross-hatched here is the readout electronics, and you have the total area of the pixel. So one of the figures of merit here is fill factor. What percentage of the pixel is actually light collecting? Now, astronomers got highly upset if they didn't have 100% effective fill factor, even though we have to put transistors in there. So we would squeeze our transistors in up here, and we would do this symmetrically. We would do this more symmetrically for a science grade device. do something like this, and then have the next adjacent pixel right here, have no filters on top of it. So light that hit like right here would actually end up being equally divided between the two pixels. That was one of the tests I had to run. The reason why for building my 10 micrometer pinhole camera with George Simmons was that basically we wanted to scan across here and see what you look at the light from here and the light collected from here as we're scanning across, and make sure that there wasn't a dip in the middle. And what we got is when you add the sum of the two pixels together, you've got a constant light across there. So we called that 100% effective fill factor. As you put more electronics in the pixel, the fill factor goes down. You're going to get a grainier image because you're going to miss some of the light in here. And with this, this is one way of kind of like fudging the fill factor thing, is I put a little micro lens right next to the array that has to be done within, right on top of the CMOS processing in the same silicon substrate. I put this little lens in there that focuses all the light that would have normally come, all the light that would have normally come down here, and focuses it back towards the pixel. So these are called micro lenses. And this is one of Guan Yang's idea. I was probably the original guy who came up with this. And he was doing all kinds of lenses on the camera and color filters. So you could get, instead of getting a grayscale image, you could get a color image by putting a green, a lens that would only pass green light on one pixel, red light on an adjacent pixel, blue, and then interleaving those. So the pixels were small enough that you couldn't see the red, green, blue, but it was kind of like those, you guys have never seen that. The old TVs from the first color TVs from the late 60s, we had one of the first ones. We're going to watch the moon landing on it, which was in black and white. But if you came up and you looked really close to the TV, you could actually see the little red, green, and blue dots. So there were tiny little filters on there that were emitting light. So it's the same kind of idea here. This is how we get color images from basically just something that's measuring the amount of light greater than 1.1 wavelength less than 1.1 micrometers in the visible, is we put a green filter, a red filter, a blue filter, a green, and we just interleave those, and we can do RGB, or you can use magenta. Oh, what are those colors?
Like cyan and yellow.
Yes, cyan, yellow, and there's another one in there. It looks like green.
Yellow, magenta are the three major colors.
Okay. So you can do it either way, but as long as you have complementary colors and blend them, as long as your pixels are small enough, you can't see it. In the old TV sets, you could actually physically see it. Yeah, that was in the days, don't sit so close to the TV, you'll go blind. And now we all sit like this, right? Never mind. Okay. So I've got this main imaging lens, and this was probably the largest part of our little tiny camera. I've got this main imaging lens here. I've got this going into the focal image sensor. This is a blow-up view of the image sensor. Inside the image sensor itself, I have these individual collimating lenses. So you need someone who has optical experience to go through and figure out what's going on here. I had George. And George would talk to me. He wouldn't talk to the mechanical engineers. That was a problem. The optical engineer wouldn't talk to the mechanical engineers. He talked to the electrical engineer. So he went through and he designed the set of lenses and diffraction gratings and all this stuff to build this spectrometer. And it's all perfect and everything. He ships them out to get them made. They're all being custom made, like a year lead time to get these things. And the mechanical engineers were working with an old spec, which wasn't the same spec George was working with. So when they got done, some of the distances between some of their gears, so where they were putting these lenses and diffractions things were off. And of course, George has to be right because he's the optical engineer, and it's going to take a year to fix the whole thing, right? So the mechanical engineers, the machinists had to go in and redo some parts to get them the actual right distances apart. Things that happen when people don't talk to each other until test and integration. That's a good lesson for your capstone project. Talk to the people who are working on the other pieces of the design and make sure you're deciding to all do the same thing.
That was why my capstone went so well, was because we all always worked in tandem.
Yes. Have meetings so it doesn't end up like me and the software engineers. Me and the software engineers kind of, and the programmers kind of work the same way George and the mechanical engineers did. I design my electronics, they go off and design their software, and they didn't match up, and it's way easier to fix the software. So everything is always a software problem. Okay. So one problem here, we don't want to miss any of the light that's coming in. We can do some optical tricks here. We can reduce this distance so we can get it all focused on the photodiode. And the ones that are next to it may have to be shifted to correct the shading. Reduce the gaps, and we can always double layer them, put 2 lenses there to make it work better. Okay, what do we have left? They were behind, but that's okay because our semester gets out earlier. The final exam is optional, and it is open book, and it's more okay. And we're done.
Cool.
Okay. Any questions, comments, Jenner? Anything you ever wanted to know about cameras?
It's not cameras. You were talking about screens earlier. How do like 3D screens work? Not like the red and blue glasses. That kind of makes sense.
Right.
Yeah,
But there's like new ones that's like clear.
I have no idea.
Yeah, I looked it up earlier that like was it the new like stunt camera called the Phantom, whatever it's called?
Okay.
It's 1 million frames a second.
Okay.
I've heard that those cameras are also like $2 million a pop.
Let's find out how much it is.
Yeah.
It's the slow-mo guys on YouTube.
Yeah, the slow-mo guys.
Yeah. Okay. Yeah. We'll talk about the one of the fast frame rate ones on here. The focal plane we had in there, we got $1 million to develop it, and we got one perfect device out of it. And that went to the people who gave us the money to build it, which was the Naval Observatory in Flagstaff. We got the slightly imperfect ones. A lot of them were like missing corners. Inside this device, inside of the Phoenix, we used a oblong array. We said, oh, it's a spectrometer. People are going to put their spectral lines down the array, and they don't care how wide they are. So what they're doing is they're splitting the IR light into the different bands and looking at the spectra to figure out what the stars are made of.
Yeah.
So that's not really an imager. And so 1024 by 512, perfectly fine. And then I talked to, like a couple of years ago, I talked to someone who used this instrument really regularly. She goes, it was really great, but I wish the detector was square. And I said, why? And she goes, you know how long he had to work to get the spectral lines lined up so they went across the array? I go, oh, we never thought of that.
The Phantom camera is 150 grand.
150 grand. Yeah, so this was, yeah.
At least the newest version of it.
That
Still don't have 150 grand.
Yeah, no, I don't have 150 grand for a camera right now. That's way too much.
Ian just went out and spent his tax refund and his stimulus check on a camera. My son.
Good camera?
It's $2,000. He's just still amazed by it, how much better the resolution is. He takes some really incredible pictures. I'm the one who said, where's the button on the camera, Ian?
I've got a cell phone. I'm good.
Yeah.
I've got myself.
I've got a little camera that I can take fairly good pictures with. If I want to take a really good picture, I just point at Ian and say, Dan, take a picture of that. Yeah, this one right here was about 1.5 million when we all got done with it. These were about $5 a piece.
Where can you buy them?
Yeah, you can't buy these anymore. You got one in your cell phone.
I just want one for just to
A tiny camera.
have a little novelty on my desk.
Okay.
You could buy tiny cameras on Wish, but like little spy cameras.
Yeah, I've got one of those in my office. I got a little.
Is it hooked up? Are you spying on people?
I know I'm not spying on people.
Come into office hours?
We were recording them. I would get more trouble than the students. I know we were going to, back when we were doing the DRAM puff, Jack and I were looking at making a CMOS imager puff out of the, we'll get to that later. I got pictures of it in here, but we can talk about it a little bit now. So right here, when I read it in the dark, if I read an array in the dark, there's a lot of noise pixel to pixel. And this is because every diode is a little bit different size. It has slightly different dark current. This is the amount of electrons that are just decaying out of that p-n junction depletion width all on their own. So the first thing astronomers do, and this is kind of like an offset correction, is they take this image and they subtract it off from itself. So they take one image and they take the dark image, they subtract the dark image off of the original image, and they can pretty much black that out to the point where you can't see it. Next thing they do is they put a lot of signal on it, and they find out that there's a whole bunch of stuff here, randomness, and then they do an offset correction, again an offset correction, just like we learned about in 380, using this, and they can get it, the gain signal to look like it's fairly uniform. When we first got the images off the telescope on Kitt Peak, they look like this. They all look like that. You know, an hour of integration and you're thinking this is just horrible. And then Mike, one of the first IR guys, Mike would sit there with his, he's a character. He would sit there for about an hour just playing games and image processing and everything on there, and suddenly the image would come out. The data was in here, but he had to run all these different fixing algorithms, noise correcting algorithms on it to actually get the real image out of it. And so our idea for a puff was we were going to just take a camera and put a cover for the top of an IC thing on top of it, tape a dead SRAM to it is what we actually did, to the top of the lens, and put the camera in the dark and take images. And yes, we got randomness out of this. The problem that I just stopped it after about 2 or 3 days, after we got the data, we didn't spend a long time on this, was that I started looking at this, and it just hit me as I knew it was wrong, is this dark current is a function of temperature.
Is it?
It's a very strong, it's one of those exponential functions of temperature. So your puff changes completely if the temperature changes. So that was not a good puff. So we went back to messing around with the DRAM. Anybody care? Anybody care how the DRAM puff works? Ben, what? Oh, okay. So it's you guys should actually understand this. Let me go through here real quick.
And Isaiah and I have
Right.
knowledge from Cambo's class. We can talk about it briefly.
Elizabeth, he talked about the DRAM puff.
Real briefly.
Oh, okay, because yeah, okay.
Just talk about how.
I thought he was ignoring us. I don't think he can. I don't think we can implement it commercially. I think that's what the problem is. Why it just is just sitting on the shelf right now.
Yeah, I think
Richard.
What's it?
Connor.
Corey was looking at DRAM hubs recently.
Okay. So basically, DRAM hub. All right, I got you, Myrna. I'm just checking attendance, Josh, in case anybody just gets bored and leaves. Okay, the DRAM puff. We know what this thing looks like. And this is an amazing thing when I had this realization here. This is tied to VDD over 2. Okay. When we were trying to turn reset off and we didn't have the source code that would allow us to do that. And I still don't think it's possible. Yeah. Did you get me to a 10? I was a little late to clap. Bryce, yes, I got you. So what we, Bryce, you're here. Okay. What we did is we couldn't turn reset off. So I started looking at this and saying, okay, we need to get a really long decay time on here. And this goes into the sense amp and compares it to VDD over 2. The pre-charged line from someplace else. The first thing was I'm just going to power it down and see what state it reads up in. And I got a whole bunch of nonsense that just varied all the time. The next thing was, okay, I'm going to power down the entire DRAM. I'm going to write 1s into the entire DRAM chip. And I'm also going to try this writing 0s into the entire ReRAM chip. If I write 1s in, because you know with this VDD over 2, it should have like a 50-50 chance of coming up at around VDD over 2. If there's no charge on this capacitor, this voltage would be VDD over 2. Some of them are going to be a little bit above, and some of them are going to be a little bit below. That didn't work so well because I didn't get a whole lot of good data out of it. So the next thing we did is we tried writing all 1s into the array, and then we did tests where we wrote all 0s into the array, and then powered it down. So you write a 1 into every cell, and you power it down, and we waited various amounts of time to see what would happen. And we found it actually, on the average, takes about 5 seconds of power down time before the 1s start decaying to 0s. Once they've hit their decay time, so each individual cell has a decay time associated with it. The charge decays away.
I think that could you use something kind of like this to have the computer determine how long it's been turned off for?
That'd be interesting.
Yes, you could. Yes, you could. That might be an interesting application. Because it's like some of the cells would take 3 hours and they would still hold that 1.
That's real good.
Yeah.
Some of the cells would take immediately, you know, milliseconds. They've already decayed. And then, yeah. And we found they discharge faster than they charge. So what we did here is we would wait a set amount of time here where we had about 50% of them would be discharged. And it was always the same 50% of the cells that would discharge faster. And then we would bring that up and read it out as a puff. Doing this in practice isn't gonna, it's amazingly, it's kind of like what we're doing on the SRAM puff, where you actually have to power down the memory and wipe out your entire DRAM memory every time you want to generate an encryption key. It's not really practical without adding a new device in and then putting a power controller on that device. So it would be kind of expensive to implement in practice. And we had better stuff coming in at that time with the ReRAM and the MRAM. So it's kind of sitting on a back shelf. But that's that's kind of an interesting idea.
I mean, I don't know what it would really accomplish. other than if it realizes that it's without power for
Mm-hmm.
5 seconds, then maybe it should try to save everything to memory, but otherwise it'll try to hold on to it for those 5 seconds or something like that.
Yeah.
From a software perspective, it doesn't really matter. You turn off the computer and then it'll
Right.
come back on.
Right, and it'll come boot back up again. Why would we care how long the computer's been off? I don't know.
It's,
Okay.
it doesn't take us anywhere.
Yeah. That's an interesting idea, but I don't know what to do with it. Okay. So, any other questions?
Why wouldn't we just use like read-only memory or some sort of puff to say like this chip is unique and it is chip number 123?
I mean, I guess
Okay, so they've got things like that. They have serial codes that are associated with motherboards, and they have encryption keys that are stored in memory, in hard memory that stays there when it powers down, non-volatile memory. But the problem is people can read those off of the memory because they're there all the time.
Oh.
Yeah, but if you're reading your puff, then you're comparing it with something else,
Right.
I imagine, to see if this is the piece that you're looking for.
Okay.
So you
So
could just look at that other thing.
okay. So you've got a server, and the server has maybe like 10K of data. It's puff data stored for each device. Doesn't take up a lot of room right there. And what the server does is it sends out addresses in your puff of where it wants you to read. So you read that puff on that addresses, and it can be different every time. You can have a different key for every communication you have. Server sends out addresses of where it wants you to read the bits of the encryption key. It reads those, and you know what your puff is. The server knows what your puff is, but you have not sent that key back and forth, and you have not stored it any place in memory. It's even if someone reads the puff, unless they have the puff and the information of what the addresses were at the same time, they would take both of those to decrypt the message, and it would only work for one message, because you can generate if you have 1K of memory, you can generate 2 to the 1024th different encryption keys from that 1K of memory.
Since you can only write to the raw read-only memory once.
Yeah, but I mean, if you store it there, then that can be read. Yeah. Yeah.
That's cool.
Yeah.
Interesting.
Yeah. So.
It's a pain on a lot of the new books right now that Apple's pumping out. Is that if you take out the hard drive and you put in a spare one, the Mac just won't turn on.
Won't recognize it.
Yeah, it's got something in there. It's probably just hard coded in, I imagine.
Right.
But
Some kind of serial number that it recognizes that particular
It's like with
device.
a lot of newer cars.
Mhm.
Now, you can't replace the computer in it unless you take it directly to the manufacturer.
To the dealer.
Not on the dealer.
Really?
I had a Volvo that they tried to replace it, and they couldn't. It's like, no, 100%.
To Sweden.
Yeah, apparently.
What's the shipping cost?
They send the computer back to the manufacturer.
not the. Well, and your keys are like that too, is because your keys actually have an identifying and an identifying key in it too, and you cannot just go and get another key made.
Yeah, it's not like
There's an electronic communication and the.
not in this truck that was made in 1994. This key cost me $8.
yeah, that or like how my dad was talking about back in the 70s. I think it was Buick had about 7 different
Okay.
key cuts.
Right.
So, and the thing is, he got an old Buick. He bought an old Buick from someone.
Uh-huh.
The thing is, he didn't have a key. So he fished around in his
And just picked a
big
view.
keys and found all 7 like variations of the key and just tried each one. And one of them worked.
That wouldn't fly today.
Yeah. Yeah.
Yeah, so I guess technically if you could, back in the 70s, you could technically take someone else's car, you just happen to have the same key cut as them.
I'm sure a few car thieves knew that.
Walk up to him, a key ring, 7 different keys.
Yeah.
No.
Well, then, yeah. Where you'd really get it would be the insurance rates. They look at the theft rates and how easy it is to steal the car, and then your insurance rates go up.
Now we just need to figure out how to emulate the key fob signal.
Oh
So you
yeah,
can press a
like
button on
how
the universal
how-
remote
how-
and open the entire parking lot.
Yeah, like how my key doesn't even have a key. It's just a fob and
Yeah. Well, my Prius was like that too, and I could actually get in the car. I could unlock the door without ever getting my keys out of my pocket. I could unlock the doors, start the engine, and everything as long as the key was close enough.
yeah.
You can figure out how to make that universal remote. 100%.
Yeah.
Yeah, but I wonder how much actual what sort of, I want to know what kind of pump car companies use.
I guess they use something.
Well,
Use
they
something.
may not use a puff. They may use a just an encryption key that's stored somewhere in memory.
Mm.
And if you know the location in memory where it's stored,
It'd be hard to find.
yeah, well,
But it could be there.
it could be there. Well, that's part of the reason why Micron, when they store memory, they, the hacker may know the logical address of the encryption key, but they never store the actual place at the same physical address as its logical address.
Reminds me of
And they actually scramble it up, and so it just looks like a big mismatch.
It reminds me
Mismatch
of
in there.
the issue I run into when I reload my computer. So I had Windows was installed on one hard drive, but somehow the key was on the key to actually make Windows work
Right.
was on a separate hard drive.
Okay.
And the thing is, the separate hard drive was taking too much power for me to run my computer. So I took that hard drive out, and then something Windows stopped working.
Fantastic.
And I'm like, what is happening? And that's why I've labeled, I put that drive in a box and labeled it stupid drive.
Well, could you do the thing where you just have the hard drive plugged in when it's booting up and loading Windows, and then,
It constantly had.
oh, okay.
You buy a second computer so you have a second power supply just for the
Well,
Copy everything on that hard drive.
until I got my hands on another copy of Windows, I bought a higher wattage power supply.
All right.
And put that in my computer, and then just continued running this bullshit system until I finally reviewed Windows. And that
Right.
computers are dumb. Computers are so dumb. The rocks that we tricked into thinking. Very complicated.
Or just doing a lot of computations. They can't even think.
Yeah.
Yeah.
For now.
I think there's more to it than people think. They're trying to model the brain and the neural nets and everything on it. And somebody came up with this thing that, well, maybe the information really isn't in the neural nets. Maybe it's in the electromagnetic fields coupling between the neural nets.
But if we can figure that out, we can make one.
Yeah, if.
That's all it takes.
Yeah, and occasionally I'll like be looking for my closet and I'll find the box that says stupid drive on it.
Okay.
Throw
Oh,
that away, man. You don't need it.
It's a monument to my hubris.
you can't, but you'll never be able to boot up that computer without stupid drive.
Well, the other drive that had Windows on it originally, I since then wiped, and
Yeah.
I'm using it as just a separate. It's basically just a glorified flash drive at this
Okay.
point, because since my computer has hot swap ports on it, I just stick it in the hot swap port whenever I need something on it, and I just take it out.
Okay.
Why you take it out?
Because I switched them out the hot swap port.
Okay.
I only have a couple of drives. Not enough for switch.
Okay.
Good lecture. Yay.
Hey, we survived. This is the let's see, get this.
What's faster side?
Just getting the NVMe drives.
True.
Where? Oh, here it is.
You're asking what's faster than a power wire?
Yeah.
Yeah.
Gold or light?
I guess, yeah. I just need a faster side.
Yeah.
Probably not the problem. You just
Yeah.
need faster. Everything else. Talker's great. Julie, do you know about General Dynamics?
In Scottsdale?
Yeah.
Yes, they make radios.
I'm working through the interview process.
Okay.
I wondered if you had any insight.
Yeah. Tyler Lee. What's his name? The class clown. All the class clowns from NAU for several years ended up at General Dynamics in Scottsdale. And that's kind of the mentality of the place, okay?
It's a circus.
It is. They build military radios. So a lot of times for NAU grads, what they're looking for is either someone who can program or someone who can do DC to DC converter power supply design or something like that. Once you get in there, you can go in any direction you want to. Oh, Keith Caldwell's down there too. Yeah, that's another one. Oh, Aaron Childers. He was the guy who named the colonel. But it's you know, you kind of like start working on something, and it's a place where you can actually be very mobile. What happened to Tyler Lee is his first job there. They basically gave him some BS thing to do, like they do with everybody, for your first job. And he got really, really bored and ticked off with it. And so he said, I want something real. And so they said, okay, we got this rack of test equipment that they want to install all over the world. You make that thing work. It's been sitting there for 6 months. Nobody can make it work. You make it work. And so now he went and did that and made the whole thing work. And now he just travels around doing the installations all over the place. And then Paul and Furman worked there for a while too. And they were designing, Furman was designing FETs, and Paul was designing a frequency splitter and combiner, basically, so you could take 10 MOSFETs, have lower gain, and have a bigger bandwidth, and you split and it's a RF design technique where you actually split the power equally between these 10 paths. You amplify it, and then you have to combine it back into one signal. A lot of geometry involved in that, and if you want to get into it's RF design. It's a whole nother black art involving Smith charts. But they have jobs like that. They have programming jobs. They have FPGA jobs. Keith went out and he just got his master's degree, and he's a DSP engineer doing the mathematical computations on the signals and things like that. So they have a wide variety of work there. And whatever you get interested in, you can kind of like shift from group to group and from project to project and get where you want to go.
I mean, if I get it, I'll let you
Yeah,
know.
Okay, yeah.
That sounds really cool.
If you get in, let me know and I'll send you the name of all the class clowns.
You'll meet them. Hey, Julie, that's why the position that I'm going for right now is something about PCB design
Okay,
or satellites.
okay, yeah. So
I could send something into space one day, like
right,
if you,
Yeah.
too cool.
Yeah.
Send Julie to space.
Well, you want to go to Mars.
yes. Watch my left pinky finger.
And it all comes full circle.
Yes.
Yeah. All right.
See, there's a point to this lecture.
I'm gonna miss this class.
I am too.
Me too.
In your course evaluate, I won't do any good there. We're as soon as I get 490 in the fall filled up, I'm gonna start. Oh, I'm not. Am I recording?
Recording for this class.